In mathematics, a matrix, or the plural matrices, is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. Matrices are used much more in daily life than people would have thought. They're in front of us every day at home, when we go to school, work, or university. In this video, we'll look at an overview of what a matrix is, what the connection between tables and matrices is, what matrices are used for. We'll look at matrix order, matrix notation, matrix equality, and we'll look at some special types of matrices. A matrix is a square or rectangular array of numbers arranged in rows and columns and closed by brackets. A matrix can be thought of simply as a table of numbers with a given number of rows and columns. I have an example here of a typical matrix. The order, which is sometimes referred to as dimension of a matrix, is the number of rows followed by the number of columns in a matrix. The order of this matrix is 3 by 4, written 3 times 4, which means 3 rows and 4 columns. The elements are the numbers in the matrix. The elements in this matrix are 21, 62, 33, 93, 44, etc. There are 12 elements in total in this matrix. Matrices are a compact form for storing data, which is equivalent to a table, but much more flexible. You have been using matrices for many years without realizing it. Consider the tables presented here. They can all be represented in matrices by extracting the numbers and placing them into square brackets. The first table looks like win, lose, draw comparison between two teams. It has 2 rows and 3 columns. We say that this is a 2 by 3 matrix. The second table looks like the ingredients for a recipe. This is a 3 by 1 column matrix, which is also known as a column vector. The third table looks like a comparison between male and female responses to a survey. This can be represented in a 2 by 2 matrix, which is called a square matrix. The final table looks like an inventory comparison between 3 stores. This can be represented in a 3 by 4 matrix. Notice how the organization of the data is maintained in a matrix form, as each number has meaning. Please note, when we use matrices, we don't include the letters next to the rows or above the columns. There are a number of advantages to matrices that lead to their use in a wide range of fields, including but not limited to in physics-related applications. Matrices are applied in the study of electrical circuits, quantum mechanics, and optics. Matrices and inverse matrices are used for programming and coding or encrypting messages. In computer-based applications, matrices play a vital role in the projection of a 3-dimensional image into a 2-dimensional screen. In many fields, matrices are used for recording the results of experiments, and matrices are used in the page rank algorithm of internet search engines, which are used in the ranking of pages, for example, in Google. The order of a matrix depends on the number of rows, m, and the number of columns, n. An m by n matrix has m rows and n columns. Here we have a matrix. It's got 3 rows and 5 columns. So we write it's a 3 by 5 matrix. Here we have a 3 by 3 matrix. It's also a square matrix, so we write 3 by 3. Here we have another square matrix, which is a 2 by 2 matrix because it has 2 rows and 2 columns. Here we have a 1 by 4 matrix, also known as a row matrix. And finally, we have a 4 by 1 matrix, also known as a column matrix. A matrix is denoted by a bold capital letter, and the elements within the matrix are denoted by the equivalent lowercase letter. Matrix A is an m by n matrix. Its elements are A, I, J, where A, I, J is the element in the ith row and the jth column. For example, we write matrix A written as a capital letter with elements lowercase a with the subscript of their row lowercase I and column lowercase j are written in this matrix. I goes from 1 to m because m is the maximum number of rows. J goes from 1 to n because n is the maximum number of columns in the matrix. This is why the element in the bottom right-hand corner is written with the subscript mn. Two matrices are equal if and only if they're identical. This means that it must be of the same order. and the respective elements must be identical. If matrix A equals matrix B, all the elements of matrix A equal all the elements of matrix B. And that's what we've written here. Here we have matrix A, it's a 3 by 3, and matrix B, you'll notice that it's the same order and all of the elements are the same. Therefore, matrix A is equal to matrix B. First, let's look at column matrices. They're also known as a column vector. A vector is an M by N matrix where either M or N equal 1, but not both. The number of rows may be any integer, but the number of columns is always 1 in a column matrix. Here are some examples. First, we have a 2 by 1 matrix, then we have a 3 by 1, and finally a 4 by 1 matrix. These are all column matrices. Next, we have row matrices, also known as row vectors. They have the same, they have any number of columns, but they can only ever have one row. Here are some examples. We have a 1 by 2 matrix, and then we have a 1 by 3, and then we have a 1 by 4. And these are all row matrices. Rectangular matrices contain more than one element, and the number of rows is not equal to the number of columns. M does not equal N. Examples include this 4 by 2 matrix and this 2 by 5 matrix. Notice that M, the number of rows, does not equal N, the number of columns. A square matrix is a matrix with an equal number of rows and columns. The number of rows is equal to the number of columns. M is equal to N. Examples include this 3 by 3 matrix and this 2 by 2 matrix. Notice that M in this instance equals N. A zero matrix is an M by N matrix which all elements are 0, usually denoted by the bold capital letter O. Here are two examples of these type of matrices. An identity matrix is a square matrix with ones on the diagonal and zeros everywhere else. It's also a diagonal matrix because all the entries are on the main diagonal. Identity matrices are denoted by a bold capital letter I. Here we have two examples of identity matrices. You'll notice that the entries, which are always 1, are on the leading diagonal, which is the diagonal from top left to bottom right. Let's look at some problems. In the following matrices, we want to identify the elements being referred to. So we've got element O subscript 3, 2. That means row 3, column 2. In this case, it's 0 because we've got a 0 matrix. In matrix B, we've got B1, 3. That means row 1, column 3. And we can see on the matrix that that's going to equal 3. On matrix A, we've got element A in the second row, first column. There's only one column, and that's going to be 4. Finally, in this last one, the identity matrix, matrix I, we've got where element in the second row, the second column, and that's going to equal 1. Let's look at a quick example. A small startup bolt manufacturer manufactures 4 different kinds of bolts. They sell bolt A for 35 cents, bolt B for 20 cents, and bolt C for $1.20. During the first 3 weeks of the financial year, they sell the following number of bolt A, B, and C respectively. In week 1, they sell 1,000 of bolt A, 1,200 of bolt B, and 200 of bolt C. In week 2, they sell 1,100 bolt A, 1,300 bolt B, and 250 bolt C. In week 3, they sell 900 of bolt A, 1,500 of bolt B, and 150 of bolt C. Construct a matrix S showing the first 3 weeks' sales. So we have matrix S. The columns represent bolt A, B, and C respectively, and the rows represent the weeks 1, 2, and 3 of the financial year. Construct a column matrix P showing the sale prices. So we have matrix P, which is a column matrix. We've got the sale price of A, which is 35 cents, the sale price of B, which is 20 cents, and the sale price of C, which is $1.20. What's the significance of 1,000 times 35 cents plus 1,200 times 20 cents plus 200 times $1.20? You notice that's the sales in the first week of each bolt multiplied by their price and then added together. And that's going to get us the week 1 sales total. In this video, we've introduced what a matrix is, the connection between tables and matrices. We've looked at what matrices are used for. We've looked at matrix order, matrix notation, matrix equality, and some special types of matrices. Thank you.